Hello and welcome to Food Safety Fridays. Welcome back. It's been a while. So it's good to be here. And today's topic is selecting the right detector for your application. And today's guest presenter is Steve Dowd, Technical Sales Manager at Eagle Product Inspection. Good morning, Steve. How are you doing?
Good. Just ready to get this going, I guess.
Yeah. And where are you joining us from, Steve?
I'm in the United States in Tennessee. So our office is down in Florida, but I'm a remote employee. So Tennessee is where I'm at.
Well, we always ask attendees to type in the chat and tell us where they're joining from. And it's always good to see, like Cindy from Lancaster, Pennsylvania, Sujit from India, Cardi from Algeria, Sushma from Germany, Walter from South Africa, Rabia from Pakistan, literally Pratik from Canada, literally all over the world. So it's great that we can all get together for an hour of education and learning. Okay, and Food Safety Fridays is kindly sponsored, and one of the sponsors is Eagle. And I'm going to play the sponsors ads now. So we're back in a couple of minutes with Steve's presentation. Okay. Okay, so I'll be back for the Q&A later. If you have a question during, just put it in the sidebar and we'll pick it up at the end. For now, I'll hand you over to Steve.
All right. Well, good morning, good afternoon, and good evening. I can see we have people from everywhere. So the session today is really about selecting the right detector, right X-ray detector, and understanding all the variables that go into not just every X-ray is the same. There's lots of different reasons why you might choose one, and some of the factors that you should know as a customer. My name is Steve Dowd. I'm the technical sales manager for Eagle. I've been with the company for about 22 years. I've been involved in X-ray for over 25 years. I've served just about every role within the company, from service to application, systems engineer, product manager, sales. So I have a pretty good understanding of all the different areas within the business. Currently, my role is looking at the customer and looking at our solutions and making sure that we've selected the right equipment to meet those customer needs. Today we'll talk about just X-ray at a glance, what creates the X-rays, some of the intricacies of detectors, and then we'll look a little bit closer at dual energy, and then the importance of image analysis, and then other factors that you may want to consider when you're selecting an X-ray. Then we'll go to a conclusion and questions and answers after that. Click. Okay. Okay, so X-ray at a glance. When you look at X-ray, or you think about X-ray, it's invisible to our eyes, but it's absolutely present. It's part of the electromagnetic spectrum of energy. So you have things like radio waves, microwaves, infrared. You have your visible light that you can see. Then you have UV light, like that gives you a sunburn. Then you have X-rays and gamma rays. As those waves get tighter and tighter, those waves are able to penetrate objects. And that's where we are with the X-ray. They're actually able to penetrate through objects. But the more dense a product is, the darker the shadow it's going to cast on the detector. So that's kind of where X-ray light sits into the spectrum. It's just outside of the area that you could see. The core components. So every X-ray company, not just Eagle, every X-ray company has a couple of key components. It's got an X-ray generator, something that's creating the X-rays. It has a detector. That's an object that's underneath. That's collecting that X-ray energy and determining how much output is there. And then you have some sort of imaging analysis software, right? So at the end of the day, every X-ray company is an image analysis company. They're going to take an image and they're going to process that image and try and analyze that image to get you a result. So it may be that you're looking for contaminants. It may be that you're looking for some other quality defect with your product, or you're looking for some sort of a lean point analysis or some sort of analysis that you'd like done on that image, right? So a quality control or a process improvement part of your line. Let's see here. So traditionally, food X-rays have been single energy X-rays, where they just have a beam with a certain spectrum of energy. They have a detector, your product passes through it, and you're looking for typically types of contaminants. You're looking for metal in your product, or you're looking for glass or calcified bone, minerals, stones, and maybe some high density plastics or rubbers, depending on if that material is doped with something. And, they're fairly, I don't want to say they're inexpensive, but on the scale of X-rays, they're probably the least expensive if you get a single energy X-ray with a line scan type of a detector. So this has been used for, probably 25 years or so in the food industry. So quite some time we've been using this type of technology. When you're looking at an X-ray system, you need to really consider, where is it you're trying to put it into your process. When we first started X-ray in the food industry, everything was at the package line. So it was at the end of line right before it went to your retail, and really looking at consumer benefits. So removing all your contaminants before it gets to your customers. And that is certainly an area to go. It's probably the least challenging area to put an X-ray system, just because you don't have to deal with the process environment, which is usually a bit more wet, a bit more harsh. And then you've got your final case inspection as well. So each of those areas kind of has its own challenges. So you need to look at what is it you're trying to do, and where is it you would like this equipment to be in your line, and make sure that you're actually able to get the benefits you're trying to get to. For example, if I'm just going to say a hot dog manufacturer, you maybe want to get the small bones out of your process. In your current process, you run the product through a grinder. The grinder has a bone collection system, and it's supposed to remove a lot of the bones. You may want to put the X-ray at the front end of the line so that you're doing a fat analysis, make sure your product is actually at the right lean point, but also to remove those big bones before they become part of your process. Or you can put it at the end of the line where you've invested some money into packaging, and you're going to remove the hot dogs that have the bones. So it's really a trade-off. Where do you want the inspection equipment, and what is it you're net trying to gain from that? So where you put the equipment is very important as well. And not all x-rays are going to be created the same. So here we have an image that's what we would call a busy image. This one happens to be like a large pasta noodle. And with a single energy x-ray, you end up with this grayscale image here, and you have some contaminants kind of embedded into the product. With a single energy x-ray, it's kind of like if you think about an old metal detector, where you kind of have a threshold at which you have to be able to go above in order to knock something off the product. Same thing with an x-ray image on single energy. You can see there's various contaminants within this, but you also see that the image itself has a certain standard deviation or a certain amount of noise or busyness to the image. So your contaminants have to be greater than this noise in order for an image analysis software tool to be able to find that. So in this image, it's a very busy image, so your contaminants are going to be a bit larger because of the image that it produced against the standard deviation of the product that it has there. So single energy is very good, but it has a lot of limitations, especially when your product has a lot of effect. Different product characteristics that we absolutely consider. What's the chemical composition of your product? Does it have a lot of salt, for example? The sodium chloride, the chloride artificially fluoresces X-ray and actually makes a darker image. How thick is your product? Is it really thin or is it really thick? That's going to make a difference on how much energy we need, how much power we need. Your packaging, does your packaging have a lot of hard edges? Like, for example, a big 70-pound or 35 kg meat carton with high carton edges, that are 7 3/4 inch thick. That's going to show up really dark in an X-ray image. And if you have a very small piece of metal right next to that dark line, it may be hard to find that smaller contaminant. Or you have, 8 inches of meat and you have a small little piece of bone next to it. That thickness of the meat is going to look an awful lot like that little small bone. We also have to consider how fast is the product moving, right? So the faster something moves means that it has less integration time on the detectors, so you don't get as much statistical information to make a good decision. Is the image busy or is it smooth? You saw that image prior was a busy image. A block of butter would be a very smooth image, right? So that you're going to have all these different variables in between. So if your product has a lot of highs and lows and different material types, it's going to be probably a bit busier. And that means that our analysis tools have to be a little bit better, or we have to look at it under multiple energy spectrums. And then where's the contaminant going to be the most difficult to find, right? If we always put it in the center or on top of the product, you're going to be able to find the contaminant pretty easily. Once you embed it into the product or you put it the opposite side of the tube, you're going to have a bit more challenge to find that. So where you put your product or your contaminant is a concern. So we want to make sure we test in all the worst locations so that you have the best detection. Second, when we boil it down, we kind of look at three main factors. You've got your belt speed, so how fast is it going? What is your product composition? And then how much energy we need. There's when you look at X-ray, there's two types of energies. You have your KV, which is your punch. So this is the kilovolts. You need a certain amount of kilovolts in order to penetrate a product. And then you have MA. MA is the statistical information, or how much of the energy that went through, how much of it is usable for you to make an analysis. So your MA is your statistics, your KV is your punch. Speed. So like I said before, the speed plays a big factor because as a product moves faster, you have less integration time on the detector. So single energy X-ray is usually really good for very high speed applications where you're not so worried about having enough power and cost, right? So everything comes down to cost at the end of the day. You can do a lot of things at higher speeds, but it costs a lot more. So linear arrays are really good for high-speed applications where you want to keep the cost down. In some products that come from the field or from the earth, where your contaminants are more natural in nature, maybe dual energy would be better for that type of application. An example of those would be bag salads. So if you buy salads from a grocery store, that's a very busy image, a lot of water in the leaves. And then the contaminants you're expecting to find there are natural contaminants like stones, field glass, metal that's kind of been thrown out in the fields with this product. Or potatoes. You know, you're going to have a lot of stones that are in the potatoes, or in the meat industry, your bones, right? So you have kind of a busy image, but your contaminants are definitely something that's going to be found in a dual energy spectrum versus a single energy spectrum. You kind of talked about it. If you have that, pasta image, that's a very busy image. This happens to be a peanut butter jar, and it's a very smooth image. In this type of product here, we have some challenges with this type of images. You've got the jar crown or the edges right here around the edge, the lip of the jar. Those would be areas that we'd be concerned with making sure that we have the right detection in those areas. So we'd mask or filter those areas and then inspect the rest of the product in different zones. So your product packaging and how homogeneous it is, how smooth the image looks to the X-ray, affects how the detection is going to be. If you have something like this, which is a non-homogeneous, this one happens to be cereal. You can also imagine if it was Raisin Bran, you would have a lot more dark, very dark areas within this. And this is more of a busy image. So you've got to be able to get the contaminant so you can find it. And again, it has to have more density, or it has to have a lower standard or higher standard deviation than your product. So in this case, we're looking for density changes. This is a grain product, so it's going to have a relatively low absorption value, and then the metal is going to have a very high absorption value. And then again, like how thick is the product? So as a product is more thick, depending on what its chemical makeup is, you may need more energy in order to penetrate that. If you have a low energy source, that's usually the best way to go, right? So the lower energy you need in order to do an inspection, the longer your tube is going to last. Typically, the main influencer there is going to be your MA. So the lower your MA is, the longer your X-ray tube is going to last, as a general rule. So if your product is really thick, you may need more X-ray energy to penetrate that. Or if it has a high salt content like cheese. So these are both two, this is a bread loaf and a cheese. Cheese has a lot of salt, so the sodium chloride actually artificially fluoresces the X-ray, so you have a much more dark image here, but it's really smooth. Here you have a thinner or a lower absorbing product here, so the X-rays kind of pass right through and you end up with a lighter image, and the contaminants show up much darker here. So either way, at the end of the day, you're trying to get the lowest amount of kV and MA in order to do the job. This is, again, some of these smoother items. When it's really smooth, objects stand out really high. I mean, they just really come through and you can see them. If you look here at the edge, there's actually a contaminant at the far right image. There's a contaminant at the very edge of that. So that would be an example of a very difficult location for us to find a contaminant, or for anyone to find a contaminant, right? Because you're comparing it to this full gray on the right of the image, but then you have a very small contaminant there at the edges. So when you're inspecting, or when you're looking at the results of your X-ray, you want to make sure that you're putting the contaminants all around that package in the worst possible case scenarios, so that you can ensure that it's going to be rejected when you're in production, no matter where that contaminant falls. Certain types of packaging are obviously much more difficult than others. In this particular instance, you see that we have a can of product with a pull tab. And here the contaminant could fall anywhere within that can. So you want to make sure that if it's under that tab, for example, you're still able to have enough contrast in order to find that. And then also at the edges or at the bottom, depending on which orientation you're looking at this type of product at. Normally this would be in a stand-up system where it'd be looking from the side, but if you happen to have maybe a case of these products running through on a flat belt, you'd be looking at it down in this orientation. So you would have areas around the tab that would be very difficult to look at, and then again at the edges it'd be difficult because it'd start to blend in depending on where that product went through and the orientation of the X-ray to the product as it was going through at different angles. You would end up getting more of these side effects occurring. So product packaging plays a pretty big role as well. And now we kind of get into the meat and bones of this particular seminar, right? So in the food industries, I don't want to say there's only three, but there's three main types. You have a linear array, which is a single stack of diodes, or it's photodiodes with a scintillator on top of it, and product passes over those in a straight line, and an image is created just like an old fax machine, where line by line, as that product moves across that, it creates a shadow and then adds those shadows across the length of that product as it was moving. Then you have a line scan indirect. We call those a TDI, or a time delay integration type of an X-ray detector. And that's going to have a scintillator, a photodiode, and then a group of these diodes in a row. That row can be edited to, more than 1, 2, 3, 4, 5, 6, 7, 8, 15, whatever. So the number of diodes after that, all of those are increasing the resolution of the image by taking the information that passes over it. You're kind of taking more data points of that same image across the number of diodes that go across it, and then increasing your resolution. The next type is one that's kind of the newest one, is called photon counting. And that's another line scan, but it's a direct conversion. So that's a semiconductor or a photoconductive material that is not needing a scintillator or photodiodes in order to do its job. So it's just a much more spatial resolution, no spread of light, blurring, a lot less noise. It's just a much faster way to do X-ray analysis. So how do the detectors work? You want your detector to have a very large dynamic range. So you want to be able to capture the full spectrum of energy that's being shot at it. So you want to have this wide range so that you're not saturating and you're not putting too little energy. So if a product is very thick or if a product is very thin, you still want to have a good image under either one of those conditions. Then you're going to have a pixel size. So this is kind of like the resolution when you purchase a TV, right? You're going to have 720, 1080, 2K, Ultra 4K. The higher the resolution, the more fine, the cleaner the image looks. The trade-off there is that the smaller the pixel size is, the less photons are going to reach that, and you'll end up with more noise, right? So you'll end up with something that has a very high resolution, but you need more energy, or you need more time, or you're going to get just more noise in general to those pixel areas. So, not everyone wants the finest resolution. It just depends on the application, which resolution you may need in order to achieve whatever specification you're trying to achieve. So most detectors, and I'd say this is probably 98% of the detectors on the market today, and that's probably going to change because of this photon counting, but most detectors are using a scintillator. So a scintillator is a type of ceramic which absorbs X-ray. It glows, and then underneath that you have a photodiode that converts that light into an electrical signal, and then that signal is sent over to an A to D converter, and then subsequently creating an image from that. And that's how, like I said, probably 98% of the market is running this way with a photodiode. Linear array, we kind of talked about it a little bit, but you have a single row of diodes with the scintillator. As a product passes through that beam, it just starts to stack this image based on how it went over. So one line of information, and it acts like a shift register. It's building an image per line. Then you have the TDI, which is a line scan type of a detector where you have multiple diodes in a row, and that product moves through this detector across it, and you have different times that the same contaminant maybe went across that detector multiple times in the array. So it's just stacking up each of those outputs and creating an image that has greater and greater resolution as it went through each of those areas. So each row is added or integrated to the corresponding pixel of the next row. So it increases your exposure time without slowing down or stopping the motion. The result is a much lower signal to noise ratio, higher resolution, and a much lower dose. So you can use lower energy to achieve the same thing that you were able to do on a line scan, a linear array. With these TDI detectors, your calibration of speed and thickness is extremely critical. So the linear array, very simple, very easy to integrate. It's probably the lower cost of all the systems. As you go into TDI, there becomes a bit more complexity. So if you have a tall product, a high product, a lot of height there, you have to make sure when you calibrate the time of this detector that you're in the center of that, so that you don't have this blurring effect that it could occur, because the contaminant at the top of this product would travel at a different rate than if that same contaminant was at the bottom of the object as it moved through. So you want to calibrate to the center so that that movement is kind of skewed one way or another on top or the bottom. Otherwise, you would end up, instead of stacking this contaminant and making a much darker single target, you would end up having this thing in the wrong time, and you would end up making a long, thinner, less dark contaminant. So timing is really critical when you look at TDI type detectors. Then we get into the newest technology, which is the photon counting. So the big thing here is you no longer have the scintillator, and you no longer need the photodiodes. So the X-ray is converted directly to an electrical signal. And that's just a much faster processing. You end up with no afterglow. So the scintillator material, when the X-rays hit it, it lights up, but then it takes a while for that light to die down once the X-rays are not hitting it. So you end up with this afterglow, and that creates a blurring image or a blurring effect on the image. So with the PXT or the photon counter, you end up with a very crisp image, and you don't need to use a physical filter to determine which energy spectrum it is. So later in a few slides, we'll actually talk about some of the physical filters that are needed in a traditional dual energy system. The drawback to this type of technology is it's very complex, and it is a higher cost, but the resolution you get on these is extremely, extremely good. It's just more complex and a bit more expensive to achieve that. Dual energy detectors. So in traditional X-ray, this is the line scan type, or the linear arrays. You have what we call, or it's a marketing word we use, called MDX, which is material discrimination type of an X-ray. And then you have DEXA, which is a medical term for dual energy X-ray absorptiometry. This is really where you're looking at different material types and trying to separate or make an analysis based on what type of atomic composition that material had. And then you have PXT. PXT is a dual energy TDI. So it's a TDI, but it's also using multispectral. So here's where we're going to talk about some of the filtering effects. So in a traditional X-ray, you have two photodiodes or two sets of diodes. You have a low energy detector, then you have a filter, typically a copper or some other material that's going to block out the low energy. And then you have a high energy detector. And normally you would have to have it curved because you want the X-ray light to hit the same diode high and low for where that beam path is going. So in this image, you have the X-ray at the top, and then at the bottom, you have a detector. And if you look at that bottom kind of image there where it shows the curve, so the X-rays are going to come out in a straight line, kind of in this cone shape. So you want to make sure your detectors are stacked in a way that they're getting the same photon going through it as it's hitting the detector. So you have to have a kind of a curved shape. So there's a complexity in how you build the system to make sure your high and low energy is actually the same diode that you're getting at both energy spectrums. And then that filter is just something you have to put in to make sure that you absorb all of the low energy before the high energy photons go through and hit that detector. So it's a bit more complex, and you actually need a physical barrier in order to see that. What we're basically doing is taking a ratio of high to low energy and then determining what that material's atomic composition is. In this case, you also are defining high and low energy by this physical filter on which photons each are going to be looking at. So you set a physical limit. So maybe the low energy is 0 to 70 kV and the high energy is 70 kV to 140 kV, something like this. And then you take that ratio and then you make a determination. What you get out of that is you end up getting your organics versus your inorganics at that certain energy. So this one happens to be a bag of chocolates, which would be a very busy image for a single energy X-ray. But once you run it through the material discrimination, what you could see is you have a piece of glass here in the middle of that. It would be very difficult for you to find it in a single energy image. But once you take out the inorganics and the organics and separate them, you end up seeing that the glass is something easy you can see. So again, all X-ray companies at the end of the day are image analysis companies. So the better the image that they have to analyze, the better your results can be. So this is one advantage of MDX versus a single energy X-ray. DEXA. So in DEXA, again, it's a medical term, but it's for how we use dual energy to discriminate different material types. We developed this for the fat analysis systems. So here we're looking for, meat type products and determining the fat or lean or moisture of that product. So we take the high and low energy spectra or information, and we take that ratio, and we have algorithms set up specifically to look for, lean versus fat. And then the residual is going to be your moisture. So we can determine moisture content, lean and fat of a product. And that's, not your traditional type of X-ray application where you're looking for contaminants. This one's actually looking to improve a process, to give the processor or the supplier more value for their product. So this is more of a value offering for a company. Again, in the meat industry, our key things here are making sure the product is purchased at the right price, make sure that they're able to blend to the right rate. They can reduce any sort of inconsistencies in their operations. They can identify preferred suppliers, meaning if I was a hamburger producer and I was making hamburger patties and I had 10 suppliers, And as I was bringing the product in, I have a certain recipe in order to make my product. I'm trying to make an 80-20 type of a product. So I bring in 90s and 50s and a lot of different suppliers. So as I put the x-ray on the front end of this, I can see that supplier A is always giving me lean, which is the more expensive product. Their 50s are always a little bit high as well. So now I have two inputs that are always high, but I'm not taking advantage of it within my process. So now I can adjust my recipe to take advantage of their free giveaway that they're giving me. Maybe someone else is always consistently right on target, and I don't have an opportunity to claim them, but I have a good product. Maybe someone else has a lot more contaminants in their product, so I want to identify them as having contaminants. So I want to maybe get that information back to them so they can clean up their process. At the end of the day, everything that I'm doing on the fat analysis system is trying to achieve a certain level of efficiency on my back end and identify my value chain to make sure that they're actually giving me the product that I'm purchasing or taking advantage of it if they're giving me something that's free, right? So here's some images of the PXT or the this is PXT. This is our newest technology. So here you would have a standard dual energy image on, it says standard x-ray. This is a standard dual energy x-ray. So this is using MDX. You can see the image here is a bit grainier on the left and a lot more clean or smooth on the right with the PXT image, where you may say, well, I can see the contaminants on both sides. Absolutely you can, but one has got more noise or it's going to be a little bit harder to find some of the real small contaminants because of the noise that you still see within that image. If you look at the standard single energy x-ray, you see this piece of meat here, but then if you look at the right side, you'll actually see that contaminant stands out quite easily. So the imaging is a lot, we just have a lot more filters on the PXT side that we're working with because we have multiple spectral of energy there. Here would be an example of chicken breast. So chicken breast, traditionally for us, we stayed away from for many years, because in order to do this in a traditional way, you needed an x-ray power that was so great that your x-ray tubes were going to burn out. Now we've got this type of technology where we can use lower power and still get an amazing image and find these contaminants that are very difficult to find without sacrificing equipment costs. So a customer would have a very high cost of ownership if they were running this in the old days, versus now your costs are, relatively similar to any other x-ray application. So by being able to filter out all this meat, you're able to just see the small little bone fragment there on the side with the PXT. If you look at these two images here, you can see a standard dual energy image. This is a fish fillet. On the top, you see that you may be able to identify that one small bone at the top center. But if you look at the bottom image of the same fish fillet, you'll see that you can easily see that one bone in the middle, but then you can also see all the resolution of the smaller pin bones as well. So while if you looked at a single energy x-ray of this, it would just be kind of really smooth. You wouldn't see any of these bones. As you go into dual energy, you're able to see possibly a bone, but really the resolution isn't enough for you to make a good decision on what to do with it. As you move into the PXT, the image is so much more clear and crisp. Now the image analysis software can make a very good decision on what is not supposed to be there. And again, I said it more than once now, is that every x-ray company at the end of the day becomes an image analysis company, right? So they're creating an image, they're analyzing that image, and how well they analyze that image is going to determine how well that product benefits you. So it may be that you're looking for, a simple diligence x-ray where you just want to kick off a piece of metal that's in your line, or something that's the wrong count, something like that. Like maybe you're building an 8-pack of hot dogs and it only has 7.5 hot dogs. You want to kick it off. It's a defect that you don't want to go to your customers. But there's also a lot of other information you can get from an image analysis system, right? So if this X-ray is in your line, you may want to look at trends within your process. So, when are these defects occurring, and what's going on here? Excuse me, just hold with me for a second. My computer's trying to get me to log in again.
Just are you okay, Steve? Yeah.
Yeah. My computer at the wrong moment wanted me to sign in again. Yeah, just of course Murphy's law. So you may want to look at trends like when are these defects occurring? So for example, we had a customer that was, they put one of these systems in, and as we looked at the data of their line, we saw that contaminants were occurring at like 9:30 in the morning and at 2:30 in the afternoon. For whatever reason, the defect rate was going up during those times. As we fed that information back to the customer, they found that the workers were actually, more excited about going to break than they were on focusing on their job. So it gave the customer there an opportunity to train their employees to take a little bit more care during this 10-minute period of time, and their defect rate went down, right? So it's more than just the removal of contaminants. You can actually learn a lot about your line and how your line is running with various conditions if you're looking at the data, right? So it's not just what is the machine physically able to do, but are you looking at the data in such a way that it's providing a benefit to you? With our software Simultask, I would say it's probably one of the, not probably, I know it is, it's one of the most advanced softwares in all of our competitors. I mean, I've got nothing bad to say about anybody, and I just know that our software is able to do a lot of things simultaneously, and it provides a lot of information back to the user, and we have a lot of different functions we could do, kind of dynamically. For example, we could look at, some smaller manufacturers or contract manufacturers may have a lot of different product SKUs running through one X-ray, and we can program our system in such a way that that product, as long as it had some differences to the every other product, we can either put it in as a product switch where we're looking at the differences of each of those things and then saying, okay, this is product A, B, C, or D, or we can use a barcode or some other tag information about that product and then switch dynamically on the fly. So a small contract manufacturer that's making 10 different products that day, he could just have the machine set up and automatically it'll switch between all those products and give you the correct inspection on the fly. So you don't have human intervention or any of these types of things that may lead to being inspected in the wrong way. Maybe you're doing a lot of cases of meat and you have a bone-in product versus a boneless product versus an export product, and you want to inspect each of those types of products a different way and get statistical information of each of those things separately. Our system can do that on the fly and then feed back that information so that you can make, again, better decisions on what your production's doing without a lot of human intervention. So factors to consider when selecting an X-ray detector. There's lots of different variations of X-ray detectors, be it 0.2, 0.4, 0.8, 1.2, 1.6, lots of different detector sizes. And you don't necessarily want to go just the smallest detector for anything that you purchase. You want to find the one that's able to achieve the job you're trying to achieve and not do a whole lot more than that, because there's associated cost. There's how much power you're going to use and how fast it's capable of going, right? So you want to look at your line, your needs, your budget, and then determine what type of system you need for your product. You don't necessarily want to be ordering from a catalog and just say, yep, I've got this problem, I just want to buy that X-ray, because there's going to be some cases where you're not really looking for it to do a whole lot more than to meet some other customer requirement for an audit, so you're going to look for more of a diligence x-ray, in which case you're not going to be as concerned with all of these things. You just want to have something in line. And it's important for whoever you choose as an x-ray vendor that they understand all of these types of things so that they could give you the best, solution for what your needs are. And that brings us to the conclusion. So again, product specification. What's the main driver for making your purchasing decision? What's your budget? Is there an ROI, or is this more for, contaminant detection or something like this? And then, I think trust is a big part of that. One thing I can tell you for sure is that every x-ray, or every piece of equipment for that matter, is going to break down at some point or another. And when you select an x-ray vendor, or any equipment vendor for that matter, do you trust your vendor in order to be there and work through it with you in a timely manner, right? So I think that, that's one of the things about our company anyway, is that, we stand behind our products and we are there with our customers. We have a good escalation process, and we have expertise to help you through not only defining what your application needs are, but also when something happens, getting it up and running again. So if you'd like to see us, you could visit us at PAC Expo in Chicago. We're going to be there this November at booth LU 7303. And now we're back to questions.
Yeah,
Anybody?
That's great, Steve. Thanks very much. Just before we move on to the questions, let me just get rid of the slides. Just want to point out in the sidebar, it is being recorded today, by the way, everybody. And shortly afterwards, an hour or so, we'll send a recording with a PDF of the slide deck, the recording, and also your certificate of attendance. But just to point out, in the sidebar under the Offers tab, you can see I've loaded their free food inspection white paper. So get the benefits of food inspection before packaging, and that's a white paper. And if you click that link, it will take you to a website. It won't close this webinar. It'll open up a new window, and you can go and download that now or later. And I'll also include that in case you miss it in the follow-up email. So I'll just leave that for a little while. But for now, let's get on to the questions. And there have been quite a few. So I'll start at the bottom. So hopefully you can see that, Steve. Marvy, is it possible to... where's that gone? Is it possible to use X-ray on sugar to detect potential powder-activated carbon on sugar?
Yeah, I think that's going to be maybe further down the line. Let's see here. Today, I think that would be more difficult. Maybe in 5 years, possible. And I say that because, right now we're using pretty much a dual energy spectrum. And as we get into more multispectral X-ray analysis, then we could make finer analysis on something like that. So I don't think right now, but maybe in the future.
Okay. We tend to get a lot of product-specific ones here.
Yeah.
No surprise. Okay. Alisa, adding on to Conrad's question, what detector would you recommend for variability in a clear glass or plastic jar source?
Again, we'd have to understand what is the size of the container and then how fast is it moving, right? So, just off the top of my head, most people in the, canning and jarring right now are using either a 0.4 or a 0.8 single energy, because the dual energy is not going to give you a whole lot of benefit, especially if you're in a glass, because you're going to be looking at trying to filter out the glass as your contaminant. So a single energy, probably 0.4 or 0.8 millimeter detector is probably what somebody would be looking at for that type of application.
Okay, thanks. Fiona, question from Fiona. How to apply X-ray detector for 360 degree. I don't know what's going on there. For how to apply X-ray detector for 360 degree closure application in singleization conveyor line, e.g. PET bottles.
I'm not sure I understand the question. Are you talking about something like a CT scanner? If so, I mean, they're going to be moving too slow to do a production line. Maybe you could do something like that for a reinspection line. But when you're looking at it, like, for these bottles moving across the line in a rigid type X-ray, so a side shooter, it's looking through all of your product. I mean, it's not like it's only looking through portions of it. So the 360 is kind of where I'm confused with your question. But I mean, we are looking through the total of your product and determining where those contaminants are. So
it's doing that from the side, basically.
Right. Typically, yep.
Okay. Okay, next one from Harish. What to consider when you do validation while you already have metal detector in place as a control for French fry industry?
I mean, we do a lot of work in the French fry industry, and each plant is going to have a certain HACCP or some sort of a CCP, their critical control point. And we always recommend, if you have a metal detector, leave that as your CCP and just make the X-ray as a added part of that. And the reason why we say to leave the metal detector as part of your CCP is because if the X-ray goes down, then you need to have another X-ray to roll in place, right? Whereas a metal detector is a whole lot cheaper to have that as your CCP and then have the X-ray as just a part that bolsters your process. But when we're looking at what do we do in the French fry industry, I mean, obviously, we're looking for stones as their primary contaminant. We're looking for, we could look for length distribution of your fries. But primarily it's the stones and glass and other contaminants outside of just metals when we're looking at the French fry industry.
Okay, that's clear. Thank you. Question from Julia. What are the standard detection limits for glass, stone, and glass jar products? Our customer wants a more sensitive tester. This is annoying. Our customer wants a more sensitive tester, but isn't this tricky if you're looking for glass in a glass jar product?
It can be. So, I mean, we do a lot of glass and glass inspections. So a traditional system would be one X-ray beam and your one detector. And as the product passes through it, you're kind of looking at it from that one view. We have systems that are 4 views. So four different views at different angles of that product. So we're looking at the crown. So the crown is really what makes it more difficult. So the bottom of the glass, and then the fact that your glass has a lot of variance, glass jar to jar has variance within that crown. So by looking at it through multiple angles, we're able to really highlight that bottom crown. And then we've written some pretty nice dynamic filters which covers the crown and moves as your crown is changing heights. So we're able to see that, because the fear would be is if you have a jar and you have a contaminant, 180 on the other side of that, you have the crown that sticks up. So if the product was here on the other side of the crown, it could hide. So if you have multiple views of that, then you can always get into an area where that piece of glass couldn't hide. So that's kind of how we do that.
Okay. Just a question, how does it affect line speed? Is there a limit? Because obviously the last thing you want to be doing is if you're reducing waste to become more efficient, etc. So I mean, did you cover that? Did you go over that fully in your presentation?
What was the question?
So line speed. So does that affect detection?
Yeah, I mean, obviously, as the product has a lower amount of time across an array, you're going to get less integration, so less information going to the detector about that. In a linear array, the time it had is the time that you have. As you go into the line scanner, TDI, you're collecting more of that information for each diode set that it goes over. So you're actually able to multiply how much time you had on that detector. So moving to TDI or something like this would be a way to increase resolution without slowing down. So
is TDI sort of always better or preferred?
I don't think there's an always scenario for anything.
Yeah.
There are times where one type of detector is going to work out better, and other times where there's just no one scenario that matches that.
Okay, got you. Marvy, would a food that has gone through X-ray detection at a low speed be considered as irradiated?
No. Not even a little bit. I mean, really, it depends on the types of power, but the types of X-ray energies that we're using, it's not even close. So that's just a no.
Yeah. Okay. Evelina, for which products is X-ray detection not recommended?
I would say that it's a tough question to answer, but in general, I think X-rays are pretty good at being able to penetrate products at about, let's just say, 8 inches in thickness of water. So I can't just give you a height, because a case of potato chips is going to have less absorption as 8 inches of solid water, right? So it's once you start getting above 8 inches of water, you start to need a bit more energy to get good statistical information. So it's in general, you just have to look at it. If it has a really super high salt content, like bags of salt, we would have to look at that. So there's some things we have to look at to determine if there's anything we can do. And then how thick is that product, for example? So what is the material makeup and how thick is that? And what is the speed that we have? Then we can tell you. So we can't just answer that as a general question, unfortunately.
Makes sense. Question from Conrad. What about products where the viscosity may differ from batch to batch, such as sauces, especially ones that include chunks of vegetables, etc.?
Yep. So, we do a lot of that type of thing already. So in that particular case, it's kind of a relative measurement. It's not an absolute measurement, meaning like if I'm looking at fat analysis for meat, I'm looking for fixed values, fixed nutritional values in that type of product, and they're going to have known ratios. As I look for something like sauces, I'm really looking for more like contaminants. And sauces, you're usually going to have filters anyway, some sort of screening in that process or not. So if you have chunks, obviously the screening is not going to work. And then you're going to have types of products. So you're going to have stones and things like that. With a single energy, you're going to see a lot of things, especially in a sauce, because you're going to be looking at it in a pipe. So you have a fixed geometry, and you have a certain amount of absorption that material is going to have within that pipe. A tomato chunk, for example, isn't a whole lot more dense than tomato sauce that's around it. So while it may be a little bit different, it's not going to be enough that we would trigger a defect for that. If you wanted us to find a defect for that, then we'd have to look really close at identifying those chunks and then how we would get those out. But in general, it'd be a relative measurement. So day to day or batch to batch, as the process changed, we'd be looking at the product and what is relative around that at that time. So it's relative measurements is how we would do that.
Okay, thanks, Steve. Sihan, detector cards have a certain lifespan and need to be replaced. Does Eagle do R&D work to extend the life of detector cards?
While this is true, I mean, we've been doing this for 25 plus years. We would see the equipment end of life before we would see this degradation of performance, honestly. Meaning that we have x-rays that have been out there for 15 years running with no degradation in performance. So in most companies, they would depreciate their equipment, 7 to 8 years would be, typical for someone to capitalize that equipment. So while this is absolutely true, we just haven't seen that in reality. Do we spend a lot of time on that? Not necessarily. We're always looking at different detector technologies, and for our linear arrays, we're looking at what types of scintillators we're using, et cetera, and making sure they're not fully hygroscopic. And if they are, making sure we have a thermal management system within our detectors that's going to pull the moisture out. So we're always looking at things like this, but we just haven't seen this to be an area that we're concerned with.
Okay. Thank you. Zafar question. Is it possible to detect internal defects in fresh produce or spoilage in products?
I think you'd be better to get a bionic nose or something, to detect that type of thing, like a Cyranose or something like that. But unless the defect was such that it made a void in the product, I think it would be very difficult for us to see that, because, if I look at vegetables, it's a high concentration of moisture, so you end up with a really dark area of that image, and spoilage doesn't necessarily make the moisture more. It may be a darker area, so it's something we can look at, but I would think it would have to be fairly, really, really spoiled for us to determine that was a non-normal distribution. But until we see that exact scenario, I couldn't say for sure, but it's possible.
Okay. And question from Prem. Is it useful in the dairy industry?
X-ray in general, yes. I mean, it really, again, it depends on what the application is and what you're trying to do. But, in some applications, we're doing large 50-pound blocks of cheese, and we're just looking for, traditional defects. In some areas, we were asked to look at the whole distribution for like Swiss cheese, to make sure that they had the proper number of holes, because there's different gradings for the Swiss cheese based on the number of holes. So, we look at that type of product for that. So it really depends on what is the application, and then we have to look at that specifically for the application.
Okay, got you. Right, we've got through all, Steve. Well done, brilliant. So, thanks very much for your time today. Great presentation and some great Q&A as well to finish it off. So appreciate your time, Steve. Yeah. Is this your first time? Second time, isn't it? I think. Yeah.
I'm not sure. I mean, I do various presentations and stuff. I mean, it's, I've been just about everywhere within the company, so I don't need a lot of notes.
Well, it's been great. Thanks very much for your time today, Steve. And
hey, thank you, guys.
Have a good weekend.
Hey, y'all do the same. Have a good weekend.
Okay, I'm just going to put your certificate of attendance in the sidebar. You can go and download that now. As I said, we'll be following up with an email shortly with the recording, copy of the slide deck, certificate, link to the white paper download. So I hope you enjoyed that and got something out of it. Appreciate your time, and sign up for next week's, and we're back on Food Safety Fridays. So have a good weekend, everybody. Take care. Bye.